Welcome back. This is discrete optimization again, the knapsack problem. And as you can see, I have a new hat. This is the branch and bound hat, something which is really useful and going to be used over and over again in this particular class. Okay, we're going to introduce branch and bound and also the value of relaxation. Okay, two very important concepts in one lecture, but still the lecture will be short. You'll see. Okay, so this is the one-dimensional knapsack. We have seen it many times. You probably start getting fed up with this particular knapsack, but you're going to see something beautiful today. Okay, so remember when we talk about dynamic programming, we talk about exhaustive search, okay? And in a sense, we have these, decision variables on top. And what we're trying to find out is the values that are possible for these decision variables. And what I've shown you during the dynamic programming lecture is that there are exponentially many of these guys, okay, in terms of the number of items, okay? But how do we, this is a way to actually build this configuration, okay? You can take the first item, and then you have two decisions, okay? Whether you take the item or whether you don't take the item. Okay? And now you have these two possibilities. And for these two possibilities, you're going to look at the second item and you can decide to take the second item or not to take it. And once again, what you get now are 4 different configurations. And now you can do the same with the third item, okay? And you get the final 8 configuration, okay? And every one of the configuration will tell you whether you choose, item 1 or not, whether you choose item 2 or not, or item 3 or not. And obviously, if I had 4 items, we would have, 16 of them, 5 items, 32, and this would grow very large. What branch and bound is about is looking at this tree and trying to explore only a tiny part of it and finding the optimal solution nevertheless. Okay? So that's what we're going to do. And we're going to show you how to do that. And the key idea is that you will iterate 2 steps. Okay? Branching and bounding. And branching is boring, right? So it's like the exhaustive search, except that later on I will tell you that there are smart ways to do this. But at this point, it's completely boring. It's like, okay, so I take an item and whether I take the item or not. That's what branching is going to be about. Okay? It's like in the exhaustive search. But then bounding is very different. It's like finding an optimistic evaluation of what you can do. Okay? So in optimization, you have to be optimistic in life as well, right? So we want you to be optimistic and find what is the best that I could ever do, okay? If you are maximizing. Or if you are minimizing, how low can be my cost, okay? So that's the kind of optimistic evaluation that we need for bounding. Okay? And I'm going to show you how we can get this. Okay? So how do we find these things? So we are going to basically take the problem and relax it. And so optimization is the art of relaxation. Okay? So you imagine yourself in this temple, and you are completely zen, and you find out how the best way you can actually relax these problems and make it easy to solve. Okay? And get an and get an optimistic evaluation of this thing. Okay? So once again, this is the knapsack, and you ask yourself, how can I relax this thing, okay? And there are not that many things in this notation, right? So in this formulation. And so you may say, oh, but what I could relax is this constraint, okay? We're going to relax the capacity constraint, okay? And then as soon as we do that, obviously we can get an optimistic evaluation of this problem. And that's pretty easy to do, right? Because essentially, as soon as you relax this, you basically assume that you can put every item that you have, that you can still select, and the items that you have already selected, and you have an optimistic evaluation. Your optimistic evaluation just, take everything you can, okay? So let's illustrate, branch and bound, and this is depth first branch and bound, using this very optimistic evaluation, okay? So what you're going to see is that you're going to see these node in the tree that I'm going to build, okay? They have 3 entries, okay? They have the value that I have accumulated inside the knapsack. They have the space left in the knapsack, and then they have this optimistic evaluation, okay? So initially, I have accumulated no value. I have, the full space in my knapsack, 10 in this particular case, and then I have this optimistic evaluation, which is, I can select everything, okay? So in this particular case, it's 128. And now I start doing things, right? I start selecting the first item, okay? As soon as I do that, I accumulate the value of the first item, 45. I take 5 units of space in the knapsack, and my, optimistic evaluation is still 128. Then I try to select item 2, but as you can see, item 2 is a size of 8, so I'm exceeding the capacity of the knapsack. That's not a feasible solution, okay? So I can't take item 2, and at that point, my optimistic evaluation is reduced to 80, okay? And I can decide to take item 3 or not, okay? If I take item 3, I get the value of 80, okay? This is 1 and 3. And if I don't take it, I get a value of 45, which is essentially completely dominated by the previous solution I found. Okay? So I know that this is not an optimal solution. Okay? Now I go back to the next part of the tree. I decide not to select item 1. So my optimistic evaluation at this point is 83. It's still better than this guy. Okay? 80, the best solution that I found. So I keep going. Okay? I select item 2. If I select item 2, I'm still 83. Okay? Then I decide if I select item 3 or not. Okay? In the first case, I get an infeasible solution. Otherwise, I get the value 48, which is also dominated by the best solutions that I have found. So, this is why I put this cross over there. Otherwise, if I decided not to take item 2, okay, so what I get is a configuration there, okay, which is optimistic, whose optimistic evaluation is 35, okay. No, that's terrible, right? So it's worse than the best solutions that I have found so far. So I can decide without continuing anything that this is not valuable, okay. I don't have to actually branch on item 3. I already know that the best I could do is worse than the best solution that I have. And this is the key idea behind bonding. Once you have this optimistic evaluation, if it's worse than the best solution you have found, you know that you don't have to explore whatever is below the tree. Now, this is an example which is terribly bad, right? Because my optimistic evaluation is so optimistic that most of the time I'm going to basically explore the entire tree, okay? But still, you can see sometimes we get a little bit of pruning, okay? But what we have to do is to find a better relaxation such that we can prune bigger part of this tree, okay? So look again at this knapsack example and think, okay, what else can I relax? Okay, I'll let you think for about 10 milliseconds, okay, and then I'll tell you, okay? Can we relax something else? And you're going to see a beautiful slide, okay? So we are going to assume that instead of packing artifacts, we are packing bars of Belgian chocolate, okay? No, this is completely different, right? So because now, when you have Belgian chocolate, let me give you a picture, okay? So because this is so beautiful, I'm already hungry here. Okay, so, and I can tell you that Indiana Jones loves Belgian chocolate. That's the best chocolate in the world, by far, okay? So this is this bar of chocolates, okay? Now, what Indiana Jones can say, I can't pack the whole thing in my knapsack, but I can break it in a piece and put it in my knapsack, right? So this is completely different, right? It's not I take or I don't take. I can take a piece of it, right? And so now, assume that my whole knapsack is built of artifacts that I can break, like, Belgian chocolate, okay? So then I get this beautiful relaxation, right? So the only thing that I did was for the decision variables, they don't have to be 0, 1. I take it or I don't take it, black and white, yin and yang, right? Only what I'm doing here is saying, but I can take a fractional value of this particular decision variables. I can take a quarter of it, or I can take half of it, or something like this, right? And so I get this optimization problem here, which is almost the same as before, except that the value of the decision variables now can take any fraction between 0 and 1. Okay? And now you can ask, but is that problem easy to solve? Okay? Well, actually, this problem is called the linear relaxation. You're going to see that in this class all the time, okay? Especially when we start looking at, mathematical programming, linear programming, mixed integer programming. And so this is a very, very important concept. So this is a linear relaxation of the knapsack. And this has a very important property is that in practice, it's easy to compute. And I'm going to show a very easy way for the knapsack. In practice, it's a little bit more complicated, but we'll cover that as well, okay? So the only thing that the linear relaxation is doing is take every value that have to be a natural numbers or an integer numbers and relaxing them to a fraction. That's what the linear relaxation is doing. It's basically relaxing the integrality constraints that you have in most of these models. Okay? So now how can we solve this? I'm going to show you a very simple way to do this, and this is going to basically be very close to some of the greedy algorithms that we have seen. So we're going to order the item by value per kilos. Okay? So this is this WI over this VI over WI ratio that I've shown you before. Okay, so basically the item that has this largest value, okay, is essentially the item which is the most valuable by kilo. And when you look at chocolate, that's what you want, right? Because you can start breaking them up. Okay, so essentially you order the item by this, and what you have to do is basically select all the item, okay, until the capacity is select all the items until the capacity is exhaust it, putting another item would go over the capacity. And for this, and once you have that, you select the next item and you select a fraction of it such that you fill the knapsack. Okay? So in a sense, you order this item, like in the greedy algorithm, you accumulate them. If the next one is going to go over capacity, what you do is you take a fraction of it such that that particular fraction is going to fill the knapsack. Okay? That's what you do. Okay? And this is essentially an optimal solution to this linear relaxation. Okay, so look at this in this particular example. Okay, so you see the various, item 1, item 2, item 3. Okay, so the first item is 45 over 5. Okay, and that gives you a value of 9 for that particular item. The second one is 48 over 8. Okay, and that gives you a value of 6. And the third one is what? Is 35 over 3, and that gives you a value of around 11.7. So the item number 3 is actually per kilo, the most valuable item, and then next one, and then next two. So what you would do here is that you would select item 1, you would select item 2, okay? That gives you 2 units for the capacity of the knapsack, and then essentially you take a quarter, because the weight of item 2 is 8, okay? So you take a quarter of the value of this guy, which is going to give you what, a quarter of that, a value 12, and the overall value of the linear relaxation is going to be 92. So 92 in this particular case is an optimistic evaluation of the knapsack. You know for sure that you will never do better than 92. Okay, so but this is much better than the relaxation that we had before, right? Where we would basically sum everything, okay, and get 130 or something, right? So here we have actually a value which is actually pretty good, okay, in this particular case, okay? So essentially the linear relaxation here is giving you a very good value for bounding the particular knapsack problem. Okay. Now, why is this correct? This is a simple reformulation of this linear relaxation. Okay. So you basically express you introduce a new variable yi, which is basically the product of vi and xi. Okay. And then you reformulate the knapsack, and what you see when you reformulate this knapsack is that all the items have the same value. Okay. They have a value 1. Okay, but what is interesting when you reformulate this problem as well is not only the values are all the same, but then this weight is basically the density, the inverse of the density that I was talking about. Okay, the most valuable item have the least weight in this reformulation. Okay, so how do you solve it? Well, it's like the greedy algorithm that we have seen before. You take the smallest item first, and when you get stuck, you take the fractional value of the last one. That's why in this particular case, the linear relaxation is actually well, the algorithm that I've shown you, select all the items until you get stuck, and then a fraction is actually computing the linear relaxation. Okay, but of course, in practice, okay, the linear relaxation is not a solution to a problem, right? Because we have this mask and there is no way we can break it. And anyway, even if you could break it, you would not want to break it, right? So essentially, we can't take a fractional part of this mask, right? You can't decide to just take the nose or whatever, right? So we have to use this linear relaxation, okay, inside the branch and bond algorithm. And that's what we're going to do. Okay, so we start again at the root. Okay, there is nowhere else to start. But we know that the optimistic evaluation here is 92. Okay, now we go on the left. Okay, so we take the item 1, same evaluation, less space in the knapsack. We take item 2, this is still infeasible. This is essentially the same as before. We get this solution with 80. The other one with 45 is dominated. But now you're going to see something really, really cute. Okay, so you go on the right. Okay, you don't select item 1, and what you see there now is that the optimistic evaluation is 77. Ooh, but 77 is worse than the best solution that I have found so far, 80. So you know that the entire tree here can be thrown away. You don't have to look at it at all, right? So you are at 77 here, and you know that anything which is below you, any solution, configuration which is below that, is guaranteed to be worse than the best solutions that you have found so far. So you can stop there, and you know that you have an optimal solution. And that's the value of a good relaxation, okay? So if you relax, relax and you do a good job of relaxing, okay, the computing job that you will have to do, the search space that you will explore is going to be much smaller, okay? And that's the value of relaxation, okay? So we'll talk a lot about relaxation and how you can get good relaxation in this class. And that's going to be a topic all the time, okay? But this is why, because if you have a very good relaxation, there are entire part of your tree that will not be explored, okay? So, and that's the critical aspect, okay? So, we have seen another hat. Whoops. Ha, that was good, right? And so we have seen another hat, branch and bound. We'll come back to branch and bound and branching and bounding a lot of time in this class. But this is essentially another technique that you can use on the knapsack problem. See you next time. Thank you very much.